All right. So thank you all for coming to today's One World Mind seminar. We're very happy to have Professor Yaniv Plan with us today, giving the talk. A little brief intro to Yaniv. Yaniv got his PhD at Caltech in 2011, and after that he joined the University of Michigan as an NSF postdoctoral fellow. And in 2014, he joined the math department at UBC, where he is currently, I believe, a Canada Research Chair. Yaniv has broad interests in mathematics of information, high-dimensional data analysis, probability, harmonic applied and computational harmonic analysis. And he's done some nice work on compressed sensing in the past, and is, I think, more recently starting to look at learning theory. So I'm very excited to hear about what he will tell us today.
All right, thanks a lot, Ryan. Hello, everyone, and thanks a lot to the organizers of this seminar. It's really been a silver lining in the kind of cloudy last year and a half or so. All right, so here you can see my title. Let me give another alternative title. Some probabilistic tools for generalized compressed sensing, which specialize well to compressed sensing with generative models. And in fact, I would say that was perhaps the first motivation for this work, that we have these nice general tools in compressed sensing that can specialize to certain settings, but it didn't seem like there was anything off the shelf that quite fit with the typical assumptions made when our signal structure is a generative model. So here we're trying to fill in that gap. And on top of that, we had some new random matrix theory, which allowed us to tighten previous results and extend them in a certain direction. So we're combining those two things together. A bit about my style and my talk. I typically get my kicks from trying to make a simple and intuitively understandable, simple to use theory that has some motivation and application. So that's what I'm trying to convey today. And because of that, I'm going to make it a little more pedagogical. I'll go through a couple of examples just to try to really get through the idea that it's simple to understand and simple to use. One last thing, I think this will be short, so please ask questions. All right. So generalized compressed sensing, it has a very simple model behind it. There is a linear model, y equals qx plus w. Q is a measurement matrix. X is some underlying signal. You might imagine an MRI image, for instance, that we're trying to estimate. W is some noise. And we somehow have to leverage the fact that X, we know something about X. It has some structure. Perhaps it's sparse, perhaps it has small total variation, perhaps low rank or low rank tensor, perhaps it's sparse in the dictionary, etc. And typically we're in the setting where we have fewer measurements than the ambient dimension. And the question is how to leverage this structure best to both estimate X and also to somehow denoise. Okay, so two questions that I'd start with about recovery of X. How many measurements M are needed, and what properties of Q and T allow good recovery. There are many lines of work on this. I bet I missed something, but here you can see there's different routes of attack for this problem. Okay, so first I'll summarize our contribution. We're going to give a general theory for recovery of X. we're going to allow Q to come from a large random family of sub-Gaussian matrices, except we're going to take a step away from the typical assumption of independent rows. And we're also going to we're going to allow the singular values of our random matrices to be far from uniform. And we'll get the optimal dependence on the sub-Gaussian norm. And we'll also allow T to be an arbitrary cone, and model mismatch to be allowed. So X doesn't exactly follow the structure, but it's close. Convex or non-convex optimization and optimization error. And the noise need not be random, but as long as it doesn't depend on the random matrix Q, in fact, we'll see that it acts as if it is random. And somehow we can still denoise. These last ones, they all appear in previous papers, but I haven't seen a paper that puts them all together. All right, so I said the measurement matrix Q should be random. So why should we think about random matrices for this problem? Well, first, forgetting about randomness for a second. You're given Qx plus W, you want to estimate X. What would you need Q to satisfy? Well, it would have to be, quote, well-conditioned restricted to T. And I'm putting a quote because well-conditioned can be defined in many ways. But one thing that we know can't happen, so let's say this is T. It doesn't quite look like a cone, but that's okay. If these are two different points in T, and I apply Q, so now T looks different. If those 2 points went from being very far away to very close together, they would now be indistinguishable amid noise, which means you would have some huge error in your estimate. So this is what we can't have happen. Okay, so somehow well-conditioned has to avoid this setting. Now the thing is, what you'd probably like is that you have your statistical problem, you have your data matrix, your measurement matrix, and you're able to take some statistic, some function of that matrix and tell whether or not you can have good recovery. That's what I would like. And I've scratched my head when I've had applied problems and wondered if I could do such a thing. The thing is, testing for well-conditionedness, or at least some version of this, turns out to be hard. So when T encodes sparsity, that's one of our important signal structures, there's negative results for being able to test for this. In the worst case, there are negative results, fine. But also even in the average case, there are negative results. That means there are clues that say for most given data matrices, there is no test that's going to tell whether or not it's well-conditioned to restricted to this set. So that leaves us in a tricky situation. If, at least in optimal parameter regimes, we're not going to be able to get a kind of beautiful theory that tells us we can take a statistic of a fixed measurement matrix and tell whether or not it's going to work well based on that statistic. What we can do, though, is prove that for a random measurement matrix, it will work with very high probability. Now, given that dichotomy, what I think is useful to do is to expand on the random measurement matrices that work so that they fit more, they can fit more of the aspects we might see in an actual data matrix and then work as a better intuition and benchmark. Okay, so that's why random. Now, why this particular kind of random, so Gaussian? The answer, I would say, is universality. So what we find is that if we look at sub-Gaussian matrices, which will be defined in a minute, they work universally over any kind of signal structure or many kinds of signal structure, which is in contrast to other kinds of random matrices. And in a sense, it's the largest such class, but there's a sense in which it's not which I'll just say in passing. There's some quite interesting work that also extends universality to much larger classes of matrices, mostly based on Mendelssohn's small ball method. That's also quite interesting. I won't go into it, but let me just say, I don't think that that route would allow for all of the assumptions and contributions that I listed before. All right, let me pause. Any questions so far?
Doesn't seem like it, but if there are, I encourage people to please put their questions in the Q&A and we will relay them to Yaniv.
All right. Okay, so let me define Subgaussian, or at least roughly. A random variable first is called Subgaussian if there is some constant k, so that it's tail bound. Probability that z, that random variable, is bigger than t, goes like e to the minus t squared over k squared. And the intuitive meaning here is that it's dominated probabilistically by a normal random variable with standard deviation k. The smallest such k is roughly what we call the Subgaussian norm. In fact, that's not quite the definition, but it's the intuitive part of it. And it's equivalent up to a constant to the Subgaussian norm. So if you see this norm psi2, that's Subgaussian norm, and we'll see it a few times coming up. So that was a random variable. A random vector is called Subgaussian if all of its marginals are Subgaussian, and in particular, if the max over the sphere of X inner product A, if this is finite, and the Subgaussian norm of A is that maximum. Okay, now our model. So here's the family of measurement matrices we look at. We take Q, our measurement matrix, to satisfy to take the form B times A, where A is a Subgaussian matrix satisfying the conditions typically that we need. That is that it has independent rows, which are isotropic and Subgaussian. I'll get to that in a second. And B is any arbitrary fixed matrix. And the point here is that by playing with B, we can introduce dependence between rows, because now we have linear combinations of independent rows. And we can also make it so our measurement matrix has a whole kind of different array of singular values, which can match what we see in data in real applications. Okay, so the important assumptions here were that A has independent rows, which are Subgaussian. The others could be played with. But anyways, mean zero, this means that if A is a row, little a is a row of big A, then its expected value is 0. That's isotropic, so expected value of A, let's write it like this. A inner product X squared is always equal to norm of X squared. So that is, it doesn't favor any direction. It doesn't make X larger in one direction than another. And Subgaussian, so A psi 2, let's say that's K, and we require it to be finite. And our goals will be an optimal dependence on B, on properties of B, and on the Subgaussian norm K. Okay, let me pause for questions. Great. Okay, so I promised examples. Here are a few. So Subgaussian matrix Subgaussian part. Here are a few
Actually,
Subgaussian.
the question, a question did appear right at the last second.
Okay.
It's in the chat. Let's see. Is the psi norm the same as Gaussian mean width?
No. They're related. So in fact, one way we could put this is by looking at sub-Gaussian matrices, we can determine goodness of recovery based on Gaussian mean width. So they are related, but they're not the same. Excuse me. Okay, good. Anything else?
Nothing else right now.
Okay, so a few A. So if it has standard normal entries, which are independent, if it had +1, -1 Rademacher entries, these would both satisfy K is order 1. I'm not being careful with constants, and that will be a theme. If it has bounded entries, then bounded by alpha, then K, that sub-Gaussian norm, would always be less than alpha. And one more question for you. What would be sub-Gaussian norm in this case, if we're subsampling from some particular basis, orthonormal basis? Well, not quite normal, rescaled the isotropic. So sub-Gaussian norm doesn't depend on which basis it is. So here's our simplest basis. In this case, just to think about, the sub-Gaussian norm looks like root n over log n. This is bad. This is huge. Well, it's not necessarily bad. This is a kind of matrix that would not exhibit universality, and it would not be a place where you would want to apply our results. It has a bounded sub-Gaussian norm, but the bound is too large. And one more, which is kind of in between Rademacher and that last one, which I'll give special attention to. If A is sparse Bernoulli, so I put a 1 with probability P, we're thinking of P as small. This one has some applications. If you take the linear model in group testing, which is a bit rare, but group testing here with some small probability, everyone's included in the group. You've got to keep P small so there isn't too much dilution. Then you get this sparse 1-0 matrix. And there are a few other applications where we see this thing. Let's see, does this fit the assumptions and what would be sub-Gaussian norm? Well, first, is this one isotropic? Actually, not quite. Note, expected value of A, the whole matrix A, in fact, is just P times the all ones matrix. And the intuitive meaning here is that every row is likely to be correlated with all ones vector. So the rows favor a certain direction, which is the opposite of being isotropic. So this isn't quite isotropic, but that can be fixed. Set a twiddle to be A minus expected value of A, which almost makes it isotropic, except with a little rescaling. There. And this is isotropic. So now this satisfies the conditions. And if you're actually given such a data matrix with a linear model, how do you get a twiddle out? Well, what you could do is consider P, the orthogonal projection onto the span of all ones vector, but the orthogonal complement of that. So a space that has codimension 1, then P times A after rescaling, in fact, would equal P times A total. And the expected value has been removed because the orthogonal projection zeroes out the all ones matrix. And what do you know? This exactly fits our model. Fixed matrix, and this is sub-Gaussian. So fits the model. So if you're actually in practice in this setting, you could apply this projection to your data. And then you can apply the theory that will come up. Actually, I wouldn't recommend applying that projection because in a sense, you've gotten rid of one measurement. And in fact, it's the one with best signal to noise ratio. You still could use this theory to say things about the null space of A, because applying a projection to a matrix only increases the null space. Typically, it would stay the same. And in fact, we did apply our theory here, and we were able to get the first optimal dependence on parameter P for null space property of this matrix in the L1 sparse set. All right. So now I'd like to give an intuition for what's to come. And we'll look at the simplest setting possible, which is least squares, where we're going to take B to be the identity. We'll take this linear model, but now y equals ax plus w. We'll assume A is Gaussian, the noise W is Gaussian, and most importantly, that T is just a d-dimensional subspace. And let's look at how well we can estimate X in this setting and how we would estimate it. And I claim that what our theory is going to say, at least on an intuitive level, is that any T, any cone T is going to behave like a d-dimensional subspace for some D to be defined. Any sub-Gaussian matrix will behave like it's Gaussian. Any noise, fixed or random, will behave like Gaussian noise. And finally, any fixed matrix B is going to behave somewhat like the identity. That last one's dubious, but we'll get to it. Okay. So how would you estimate X in this linear model? You would just use least squares typically. So you would take it to be argmin X prime in T, our subspace, AX prime minus Y, 2 norm. So A X hat would be the projection onto AT of Y. Let me just call that P Y. And then we would see, well, let me draw a picture actually. If this is AX and this is AX plus W, then this would be AX hat. Now, we would see the error would look like as follows. AX hat minus AX would just be P applied to W. Now, if I take random noise and I project it onto a low dimensional subspace, in this case, A times T will be a d-dimensional subspace, what happens to that noise? What happens to the size of that noise? Well, most of it gets projected away. And the size goes down by root d over m, roughly. The dimension of the subspace you're projecting onto divided by ambient dimension, which you could call square root of 1 over oversampling factor. And this I would call denoising. Denoising by using signal structure. And this is with high probability. And the left-hand side, ax hat minus ax, this will be roughly, for a Gaussian matrix, x hat minus x 2 norm, but multiplied by root n. This is with high probability, assuming that you have enough measurements. So m is bigger than d. And put this together, x hat minus x 2 norm is going to be roughly root d over m times the norm of the noise. All right, so take that as your intuition and let's see if we can extend it much more widely. Let me just say one thing. What if x actually wasn't in the subspace? What would happen there? Our picture would look like, let's say, x now equals x naught plus r, where x naught is in T and R we think of as some residual. Then AX naught would be in the subspace A times T. We'd have some extra residual here, AR, and then plus the noise, AR plus, oops. AR is this vector right here. This is W. And it's the same story as before. In fact, you can just absorb AR into the noise, except one thing could go wrong. If you picked R or you picked X, worst case, depending on the random matrix A, you could pick it in a way so that that residual got blown up and would increase your final error. So what we're going to assume now in today's talk that avoids that is that your signal X is not dependent on your random matrix A. There's a fixed X, and then you choose your random matrix, and then there's no problem here. Absorb AR. All right. So now, if we want to move beyond subspace, and this goes to that question, Gaussian mean width, what replaces d when t is an arbitrary cone? Here, I'm going to use a variation on Gaussian mean width, Gaussian complexity, which is just given a set, the Gaussian complexity of that set is this expected supremum of x in that set, x inner product g, where g is a Gaussian vector with an absolute value. And we're going to, this is a very well-known quantity, which I won't give much intuition for, but you could certainly read about it in Verschinen's book. And we'll write d of t is the Gaussian complexity of t minus t intersect the sphere squared. Let me just say one thing in passing. The theory that I'm presenting today is a scale invariant theory. That is, it will be uniform in a sense, depending on noise and depending on the position of x. Because of that, for this theory to be useful, t has to act low dimensional at all scales. In particular, that if t contained any full dimensional ball, even if it's an arbitrarily small ball, our theory would look in the worst case of that setting and wouldn't be very helpful. So this theory will be helpful when t doesn't contain any full dimensional Euclidean balls. So for instance, sparse vectors, low rank matrices, range of a neural net would all satisfy that. Okay, so let's move to B as the identity and look at what we get. So we're gonna, again, consider a version of least squares, restricted least squares, restrict to this set. And it's just as in the subspace case with a Gaussian matrix, except we replace dimension of subspace by this d of t. here, there's this dependence on the sub-Gaussian norm of the matrix. If the matrix had been Gaussian, we could remove this. But to generalize, we have this k squared log k dependence. And in fact, that turns out to be optimal in a sense. That took a bit of work. And previous results had something like k to the fourth or even k to the sixth there. And even this log factor is optimal. Here, this is as before in the subspace case, and we would have gotten this in the subspace case if I'd finished it off. This distance from x to t, that is the smallest, if you take x and it's outside of t, the Euclidean norm between x and the closest point in t. Okay, this heavily relies upon some recent random matrix theory. I just want to point out the amazing contributions of the students involved. So what set us on this track was Chris Liao's homework assignment answer. Mayrabian postdoc, I don't think we could have done it without him. I won't mention, but of course, Christian was important. Xiaowei Li for this optimal dependence on k squared was really vital. It wouldn't have happened without him, at least not the same way it happened. Similarly, without Jiang, who really got this problem going. All right, and let me mention in passing, if you can't exactly optimize least squares, then you get a little, this scales well with the optimization error. All right, so that's if B equals identity. What if B does not equal identity? So we're back to this setting. So before we asked, one would ask how many measurements are needed to estimate X. Now that question needs to change to what properties of B would allow good estimation of X. So let's think about this. If B were the all zeros matrix, of course, we could not estimate X. If B were a projection, say, onto one dimension less, it would be as if we got one less measurement. And more generally, if B has, say, singular values that are decaying, you would think maybe for the large singular values, that's like one measurement. And as the singular values go close to zero, those measurements don't count anymore. Now, I should have mentioned the measurement matrix of B times A would typically have singular values that look just like the singular values of B, because A, when it's random, will typically look like a rescaled orthogonal matrix. Okay, so given that, what we find replaces the number of measurements now is what's called the stable rank of B. This stable rank, B Frobenius norm divided by B operator norm squared, is always less than the rank. When all singular values of B are equal to some constant or zero, then it's exactly the rank, like for a projection. And if the singular values are decreasing, then it will be below the rank depending on the rate of decay. So again, when B equals I, M played this prominent role, number of measurements. Here, number of measurements had to be bigger than dimension, and we denoise depending on number of measurements. When B does not equal I, what replaces M, number of measurements, is stable rank. Except for one thing here, we also have to multiply by Frobenius norm of B in our kind of denoising part of the error bound. And that's because if you just rescale the matrix B, it changes the signal to noise ratio. So this absorbs that rescaling. All right. Any questions before I move on?
Oh, We're not seeing any yet, but if any come in, we'll certainly pass them along.
Okay. All right. So continuing. So let me work out a few special cases. I'd like to make the argument that this theory is really intuitive and simple to use. So I think the easy way to make that argument is using it a couple times. We worked out the dimensional subspace before, but let's actually check this theorem in that case. So the key to using this theorem is to calculate this d of t. Recall that was Gaussian complexity, t minus t intersect the sphere squared. So for a d-dimensional subspace, what does that come out to? So t minus t, if you're a subspace, is in fact just t. And by rotational invariance of Gaussian distribution, any d-dimensional subspace can be replaced by any other d-dimensional subspace. So let me just use the simplest one. Span of E1 through ED. These are canonical basis vectors. Now this Gaussian complexity works out to, now that we're looking at span of E1 through ED, we can just restrict everything to RD. So expected value over the max in a d-dimensional ball of X inner product G, absolute value. And in fact, this just becomes, well, what maximizes this inner product? It's when X is exactly in the same direction as G. So this becomes the norm of G, expected value of the norm, which then, let's be precise, by Jensen's inequality, this is less than expected value of norm squared square rooted, which is precisely root D. D, little d being the dimension of the subspace. So our d of t, in fact, will be less than the little d dimension of subspace. Okay. Less than and almost exactly equal to. One more, a little bit juicier. Low rank matrices isn't very hard to do either. So if T is N1 by N2 matrices of rank at most R, T minus T would be the same, but rank less than or equal to 2R. Now this Gaussian complexity, here we're thinking of the sphere for matrices, so Frobenius norm equal to 1. That would be the expected value of the max for X in this set. X is now a matrix. X in inner product G. G is a matrix. So by inner product trace of X transpose G. This will be less than the expected value of the max over this set of nuclear norm of X times operator norm of G. If you don't know what those are, don't worry too much for now. Nuclear norm is like one norm, but on singular values. The nuclear norm, max over nuclear norm now comes out. So, and the nuclear norm of a low rank matrix is always bounded. So this becomes less than root 2R, that was bound on the nuclear norm, times the expected value of the operator norm of a Gaussian matrix, which is a very well studied quantity. And this is roughly less than root 2R N1 plus N2 square rooted. So RD in this case is roughly less than 2R N1 plus N2. T minus C. Dania, thanks for the question. That's the Minkowski difference. So take every point in T and subtract every point in T. So X minus Y for X and Y in T. Thanks for the question. All right, one more special case, range of an expansive neural net. So the idea here is there was some signal structure, but we didn't know what it was ahead of time, and we learned it. And now we know that it's approximately in the range of some neural net. So G is what we will call our neural net. We'll look at ReLU's activation functions, and T, our signal structure, is now the range of this learned neural net. This one takes a little bit more work, but it's not too bad. So again, let's capture this Gaussian complexity. So for, at least in the case of ReLUs, what I think is the most straightforward way to do this, ReLUs and any piecewise linear activation function will lead to the range of the neural net belonging to a union of subspaces. And then T minus T will also belong to a union of subspaces. And you can count how many subspaces there are and what their dimension is. And this has more or less been done. I'm not sure if anyone quite got the log factor right. Maybe they did. What you can find is that it belongs to a union of subspaces, each of dimension less than 2K, and that the number of subspaces, well, its logarithm satisfies this, that it's less than K. This D, I'm sorry, is different than before. This is the depth of the neural net. Times a logarithmic factor. Here, this N is the geometric mean of the widths of the neural net. Okay, so just to show that Gaussian complexity is easy to work with, if you know that your set belongs to the union of sets, then it's easy to bound the Gaussian complexity using this lemma. The Gaussian complexity of a union of sets is always less than the maximum of the Gaussian complexities of a particular set plus root log of the number of sets. Putting that together with this lemma above gives Gaussian complexity for a neural net, T minus T intersect the sphere, is less than, let's see, root 2K for the max of Gaussian complexity because of this, the fact that they are subspaces. We just worked that out. Plus log of n, that's square root of k d log of 2n bar over k. And then you can apply the theory off the shelf. Okay, let me just say something in passing. Range of a neural net is not convex, so it would be better to look at a theory that does not assume you get an exact solution to this argument. Instead, that you can approximately optimize it. That is, x hat satisfies 1, x hat belongs to this range, x hat is in T, and 2, a x hat minus y, not a, q x hat minus y, 2 norm squared is less than min, x prime and T of q x prime 2 norm minus y squared, plus some error, let's call it epsilon squared. Okay, so if you make some error in optimization, this doesn't kill you here, and you get the exact same theorem, but with an extra term depending on that error. All right, I'm gonna speed up just a little bit. I said compressed sensing, but I haven't talked about anything about convex relaxations. Let me just say how you could do that. You can still apply this theory when you're, you use L1 minimization with sparsity or nuclear norm with low rank. You would no longer look at T as the signal structure, but some sort of convex proxy that allows you to estimate that. And now the cone that you would look at is not T minus T anymore, but the cone made by taking X and subtracting off your convex ball. So now we have a different cone. So you would replace your D of T, not Gaussian complexity of T minus T intersect the sphere squared, but Gaussian complexity of T minus X intersect the sphere. And of course, now this actually depends on X, but you could say in this set of the sparsity setting, you can uniformly bound this for any sparse vector, provided that it's appropriately scaled. And another example for nuclear norm with low rank, this new D of t is just like the old D of t. It again is roughly equal to R times N1 plus N2. And if I were to boil down the essence of the theory of compressed sensing, it would be that you can use this full dimensional convex ball, optimization over it, and you can still find this scale invariant low dimensional cone that characterizes how well you can estimate X. I guess I would combine that with the fact that that cone acts low dimensional as long as you use a random matrix to estimate. All right, very quickly now. There was underlying random matrix theory that was quite important for this. Worked out with Jiang Li and Guillemaz. And the key here, this is something that controls the conditioning of our random matrix B times A. And by conditioning, I mean that it doesn't overly increase or decrease the norm of any vector in T. Here, in fact, this is almost the expected value of the A x2 norm. And you see this K root log K right here. It turns out that is the optimal dependence on the sub-Gaussian norm. And its optimality, in fact, whoops, should be an expected value here, or with high probability. Oh, there it is. This optimal dependence was worked out by Jane and Vuong and the rest of us as a summer project. They just ate that one for breakfast. I'll give them lunch, but someone else should give them dinner. And this also builds a lot on some previous work with Liao, Miao, Robbie, and Verschinen. And very quickly, underlying the random matrix theory, there's random vector theory. So we had to specialize and improve Bernstein inequality for our setting. So Bernstein inequality tells you about the tail bound of a sum of random variables under various conditions. The conditions that popped up for us were that those random variables had bounded first moment and what's called the psi1 norm, bounded by k squared. And you can imagine why that would pop up if you look at these random variables as generated by the sum of the entries of A times X squared. So when you square sub-Gaussian, you get what's called sub-exponential, and you look at the sub-exponential norm. So in our setting, we had a control on this psi1 norm, we had control on the first moment, and if you optimize based on just those two, it gets you this k squared log k, and that's how we got that perfect dependence on sub-Gaussian norm. And new Hansen-Wright inequality, just for those who have seen Hansen-Wright inequality, and this is how we got that deterministic matrix B in there. All right, and that's it. But there's something I'd like to ask the audience. So one thing we did here, we looked at measurement matrices that took the form B times A, where B is fixed and A is sub-Gaussian. In my opinion, the big benefit from that is that you can now play with singular values of your random matrix, and then if you have your fixed data matrix in your problem, you could ask, how well would I have been able to recover X if it had been random with similar singular values? You can look at this theory to answer that question. That's what I think the contribution is. Others who I've talked to are dubious on that. Another possible contribution is there are some fixed some problems where you actually really see B times A, where A is random, like the one mentioned above. And one other contribution is that we're taking a step away from the setting of independent rows. What I'd be curious about from the audience, what you think. Like, do you agree with me about this contribution, or do you know other settings where this model B times A would be important? All right, that's it. Thanks, everyone.
Thank you, Yaniv. That was a really great talk. I would like to ask the audience to please put in your questions into the Q&A, and we'll then ask you to unmute and ask them yourselves. In the meantime, I had one quick question about the neural networks example. So you had this this result about, well, if I can't solve the problem exactly, then I have to eat this epsilon squared in the error bound. And I'm wondering whether you've thought about if there's any hope in the neural network case to get some control over this epsilon.
Well, okay, so there's some pretty nice theory on cases when you actually can optimize, but it's under a pretty big assumption. So there's a couple of papers. In particular, I point to Paul Hand and Varninsky. Where was it? Can't find it. Oh, there it is. That say that even though this is not a convex program, there's a version of gradient descent that actually can converge to the optimal solution, but it has to make the assumption of random weights. And in fact, we actually have something like that. We submitted to NeurIPS as well. So if you make a really strong assumption, you can prove that gradient descent or other algorithms can exactly solve this. But I think it's open in general. So I don't know in general if you can control that epsilon, at least in theory.
Panelists, do you have any questions for Yaniv?
Oh, I just had well, first of all, nice talk. I also just had a clarifying question on the neural network example. There was a parameter capital N.
Yeah.
Okay. That's specific to this example, correct?
Yeah.
Did I
So
miss something? Okay.
Here, let me say where that comes from.
Okay.
We want to say how complex the range of a neural net, how large is this Gaussian complexity for us. The way we're going to do that is by containing the range of the neural net in a union of subspaces. There are a ton of those subspaces, but actually not too many. And this N is a bound on that number of subspaces. And indeed, it depends on the depth of the neural net and the widths of the layers and the code dimension. But at least this bound depends pretty simply on those parameters. And the important one is the code dimension. This dependence on depth, I don't know if I think that holds in worst case, but I'm not sure if it holds in general case.
I see. Okay, cool. Yeah, that helps a lot. Thanks for that clarification. Yeah. There's a question in the chat regarding the controlling of the epsilon parameter that you were just discussing. Does that need to be thought of in terms of the number of nodes or the number of layers of the network, or simply make it smaller than some absolute threshold?
Well, I guess, okay. I guess that could be interpreted in a couple of ways. So the first question you could ask is, when can you prove that you can actually optimize and then in fact take that epsilon to 0? When you assume random weights, of course, there are other assumptions, and mostly they assume that the neural net is sufficiently expansive. So the more expansive it behaves, I guess the better it's conditioned in a certain way. The other thing you could ask is, depending on nodes, etc., how much do you pay for this extra error incurred by incorrect optimization or imprecise optimization? Well, I guess we can see by looking at the theorem. Where was it? Here. Well, this isn't a very deep answer, but you know, if this term is smaller than the other terms, then you don't pay too much.
Great, thanks.
I guess last chance to ask questions.
I have a question. Can you tell us a little bit more about the group testing application?
Yeah, okay. So, well, let's see, where was it? Okay, so in group testing, it's very natural to look at a matrix of this form, because you're grouping people together. A 1 corresponds with someone being in the group, 0 corresponds with not. You know, you don't want to put too many people in a group because that would dilute the sample too much. Apparently that's a problem. So it would be natural to look at a matrix of this form. What is not typically assumed, was occasionally but rarely assumed, is a linear model. So, so I would say our theory would apply to a rare model for this setting. Did that answer or not answer the question?
So what, sorry, I couldn't hear. What did you say? That your model will what?
Oh, our theory would apply to a rare model for the group testing setting. Because linear model is typically not assumed. Typically it's more binary, right? Either someone was infected or someone was not in your group.
Yeah.
All right, I guess if there are no more questions, we can thank Yaniv one more time for a really nice talk.
All right, thanks for having me.
Thank you. Yeah, I really enjoyed the talk.
And thank you all for attending.